In this lesson, we're going to look at how an operating system manages memory. Now, if you cast your mind back a couple of lessons, you will remember that an operating system deals with three major components. They are the CPU, RAM, and input and output devices. For the purposes of our course, we just need to deal with process and memory management. And in memory management, you need to understand how different techniques such as paging and segmentation work, and how different page replacement algorithms could be used to create virtual memory, where we could use a part of the secondary storage like a hard drive or an SSD to complement the physical RAM that is in the system. Now, this part of the syllabus is very text heavy, and there are a lot of new key terms which you might encounter for the very first time, so you need to know their meaning. Things like paging, page tables, segmentation, segment map table, translation look-aside buffer, and so on. So it's essential for you to take some time and record these key terms so you can reference them when you encounter them in the lesson. So do pause the video and jot these down. We're going to start off with optimization, which basically is a function of memory management which decides which processes should be in the main memory and where should they be stored. Paging is a technique which divides up physical memory and logical memory, which basically is storage on your SSD into fixed size memory blocks. The physical memory is obviously the RAM, the logical memory is the address space that an operating system perceives to be the main storage, and it could be something that could be on a SSD or HDD or even a USB if needs be. Frames are fixed size physical memory blocks, so when we take the RAM and divide it into equal size fixed blocks, that they are called frames. And the logical memory blocks, which basically is your SSD side of memory, is divided into the same equal size chunks, which are called pages. The page table then maps these logical addresses, which don't actually exist, they're not really RAM, to actual physical addresses. So you get an extension list where you can say, well, okay, if you had 1 to 1000 addresses of the physical RAM or the physical memory, you can then extend that from 1000 to say 10,000 of the logical version. So you can use some of that hard drive space or the SSD space to create a pseudo kind of RAM. Now, the page table can also contain other data such as page number, flag statuses, frame addresses, and time of entry perhaps, but we'll look at all of that in due course. The term dirty is used to describe a page in memory that has been modified, so it might need to be written to the hard drive or the SSD. And the translation look-aside buffer, TLB, is a memory cache which can reduce the time taken to access a user's memory location. It's just a small little buffer in a way that will store information between the logical and the physical. Now, we'll deal with the rest of the key terms in due course, because to keep the length of these lessons short, we'll divide them into three chunks. So let's start by looking at paging in a bit more depth and the concept of maximizing memory. Now, memory, just like storage space, is finite. It tends to be very expensive compared to storage space, and what happens is, just like storage space, if you're constantly reading and writing data, it can become fragmented. Now, to overcome this problem, the operating system has built-in tools to manage memory, and these determine which processes should be in the main memory and where should they be stored in the main memory, and this is called optimizing memory. The operating system determines how the memory is allocated when a number of processes are competing for it, because remember, memory is finite and you can run out of it, and that could lead to crashes. So when a process starts up, it is allocated some physical memory. When it's completed, the OS then deallocates that memory so it could be used by another process. And there are multiple methods of allocating and deallocating memory, and the most simplest one is the single contiguous, which means all together, allocation. And with this method, all of the memory is made available to a single application. Now, you can see the problem with that if you've got a big application, it can take up all of the RAM, and that means the other applications or the other processes that might need access to memory can't get access, and as such, they won't be able to run. So the operating system uses a technique called paging to ensure that it can optimize the use of memory. And in this particular process, the RAM, or the available memory, is divided into equal size chunks, and these are normally called frames. The process is also divided into equal size chunks, and these are called pages. So you can load these pages into the frames because they're all equal sized. You can load all the pages up. For example, if you've got one application in a contiguous block into these frames, that's exactly the same as single contiguous allocation, and it's not very efficient. The most flexible approach, though, is that you can use virtual memory, which means that you divide the RAM into equal size chunks, which are frames, remember that, and then you divide some space on your hard disk drive or your SSD into equal size chunks called pages. And the programs or the processes can also be divided into these little pages, and then they could be loaded and unloaded from RAM as necessary. But at the same time, if another process needs access to RAM and you've got a big program already existing in RAM, you can then load and unload unused frames, and you can keep swapping between program 1 and program 2 depending on the need, and that's called paging. So in a virtual memory system, the address space that the CPU uses is actually larger than the physical main memory space because you've allocated some SSD or hard drive space as virtual memory. So the computer actually thinks the RAM is much more than it actually is. And this requires the CPU to transfer address values to a memory management unit that allocates a corresponding address on a page, because as we were talking about, say for example you've got 1,000 addresses in physical memory, then allocating a huge amount of space on your SSD could lead to an extension. Suddenly you can end up with 10,000 addresses, and all of these addresses need to be recorded somewhere. So the starting situation is that the set of pages comprising the process are originally stored on disk, and one or more of these pages are loaded into memory when the process is changing to the ready state. So remember process management, we've just moved the process into ready state. These pages are loaded into RAM. So when the process is dispatched from the ready state to the running state, the process starts executing and the data or the instructions are fetched from the main memory. So a program is allocated a number of pages that is usually just larger than what is actually needed, and that's to create some flexibility and perhaps have a bit of a buffer between different programs or processes that are being stored in memory. So when a process is executed, process pages from logical memory, which is your basically hard drive space, are loaded into frames in physical memory, and a page table is used to organize all of this, and it uses page numbers as an index. So each page that you created, and now remember, a page is part of a program, it could be instructions or data, and it's given a page number, and that's the index or your key field. Each process has its own separate page table that maps logical addresses to physical addresses. And the page table will show page number, flag statuses, page frame addresses, and the time of entry. And the time of entry is very important when considering page replacement algorithms, because some page replacement algorithms could use the timestamp to work out which pages were loaded when, and it might be the oldest page is replaced first, and so on. Now on screen you will see an image on the right hand side which lists down most common flags and their statuses, and there's a description of that particular state. Now these flags are part of the page table, and it's important for you to know how these are used. So if you look at flag P is equal to 0, which basically means that the page is present on your hard drive and it's not yet present in memory. P is equal to 1 basically means the page is present in memory. And similarly, if you look at the D flag, D equal to 0 means that the page is unmodified. That means it's not dirty. That means it's the same as the version on the hard drive. And if D is equal to 1, that means that there has been an update in RAM and it might need to be written to the hard drive. These flags are very important because they allow you to optimize the reading and writing of pages to main memory and back again. Now on screen is an example of how a page table connects physical and logical addresses together. Each entry in the page table points to a physical address that is then mapped to a virtual memory address, and this is formed from offset in page directory plus an offset in the page table. What does offset actually mean? It means that there is a slight difference from the actual sequence that's stored in logical memory, because physical memory might be fragmented. Imagine that you were trying to locate a house in a city, and imagine that each house was given a unique number. Now you can imagine that the number of houses would soon get very large and very confusing. Now imagine that you introduce the concept of streets. The house numbers now become a bit more manageable as you group them into chunks. So streets are basically your page number, and the house number is your offset address. So in our particular case, 0 is our page number, and within 0 we're going to have multitude of offset addresses because you're going to have multiple instructions in that page. That's what we mean by offset. Now, the role of the page table is to simply map these into physical frames. You'll have the page number and the equivalent frame number. Now, you can see that due to fragmentation, you don't get a contiguous block in physical memory. However, the page table can be used to locate the different parts together. Page 0 is reference to frame 1. Page 1 is reference to frame 4, page 2 to 3, and 3 to 7. That allows the operating system and eventually the CPU to locate where the data is. Now you can allocate the amount of hard disk space or SSD space that you want to virtual memory, and that makes the page table bigger. And eventually you'll probably find when we do discuss virtual memory in a bit more depth, the bigger you make this memory, the more swaps that will need to happen. Pages will need to be read, written to, and that means that a lot more time swapping these pages and frames might happen instead of actual processing. But we'll look at all of that in a later lesson. For now, that's all for today. Hopefully you understand how operating systems manage memory, how paging works, what is the role of the page table, and what is the purpose of flags in a page table. That's all for today. I'll see you in the next one.